Today, we're going to look at a set of tools so powerful they can figure out the peak of a roller coaster, they can model the weather, and they even run the AI on your phone. And no, I'm not talking about wrenches or screwdrivers. I'm talking about ideas. Ideas from calculus and linear algebra. And you really don't need to be a math genius to see just how elegant they are.
So let's start with a problem. Imagine you're designing a roller coaster. You absolutely need to know the highest point of every hill, right? Or what if you want to find the exact moment a company's profit is at its peak? How do you find that one single perfect spot on a curve?
Okay, now let's make it even crazier. What if you're trying to model something really complex, like the global economy or the weather? You're talking about hundreds, maybe thousands of things all connected, all described by their own equations. How on earth could you possibly solve all of that at the same time?
Well, the answer to both questions is that you don't just throw more computing power at it. You don't use brute force. You use a specialized set of tools. And today, we're going to pull a few of these incredible tools from our mathematical toolbox.
First up, let's grab our first tool. We'll call this one the language of change. Because that's exactly what it is. It's all about understanding how things move, how they grow, and how they change from one moment to the very next.
At the heart of this tool is something called the derivative. And honestly, the best way to think about it is like a speedometer for math. You know how your car's speedometer tells you your speed at one specific instant? Well, a derivative does the same thing but for any function. It tells you the exact slope or rate of change at any single point you choose.
Okay, let's put this tool to work. How do we find the absolute bottom of a valley on a graph? Well, just think about it for a second. When you're at the very, very top of a hill or the absolute bottom of a valley for just that one tiny moment, the ground is perfectly flat, right? The slope is 0.
And that simple idea gives us our whole strategy. First, we use our tool, the derivative, to find a formula for the slope at any point. Then, we just have to figure out where that slope is exactly 0. That gives us our flat spots. Finally, a quick check tells us if we found a peak or a valley. Simple as that.
So let's try it. Take a function like f of x equals x squared minus 4x plus 1. The derivative, our magic slope formula, turns out to be just 2x minus 4. And that's the beauty of this tool. It takes a complicated curve and gives us a really simple straight line that describes its slope everywhere.
So when is 2x minus 4 equal to 0? Well, that happens when x is 2. And just like that, our tool has found the exact location of the bottom of that curve. No guesswork, no trial and error. We know with absolute certainty that the lowest this function ever gets is -3. That's precision.
Okay, that first tool was perfect for looking at one thing changing at a time. But what about that weather problem where you have hundreds of variables all tangled up? For that, we need our second tool. Let's call it the data organizer.
This tool is the matrix. And at its core, a matrix is really just a grid of numbers. That's it. But don't let that fool you. It's an incredibly powerful way to bundle up a ton of complicated information and handle it all in one go. You can think of it like a spreadsheet, but on steroids.
Look at this. On the left, you've got a messy system of equations. X plus y equals 5, and 2x plus 3y equals 11. But with matrices, we can just pull out the important numbers and pack them into this single super clean equation on the right. It's the exact same problem, just beautifully organized.
And the strategy for solving it is just as elegant. We start with our tidy equation, ax equals b. Then, we find a special matrix called the inverse. You can think of it like division. If I told you 2x equals 10, you just divide by 2 to find x. The inverse matrix does the same kind of thing. It's an undo button that lets us get x all by itself. And computers can do this in a flash for thousands of equations.
And boom, we apply that inverse matrix, and it just hands us the answer in one clean package. X is 4 and y is 1. Now, for 2 equations, you could probably do this by hand. But for 100 or 1,000, this tool is pretty much the only way to go.
All right, time for our final tool from the box. This one's for when you need to add up a whole lot of things. And I mean a whole lot, maybe even an infinite number of things, to find a grand total. This is the grand accumulator. This tool is the integral. And if the derivative was all about finding the rate of change in one instant, the integral is its exact opposite. It's about summing up all of those tiny little instances to find the total amount. It's how we find the area under a really complex curve or the volume of a strange shape.
So, since it's the reverse of the derivative, we can ask a new question. Let's go back to our car trip. If the derivative is the speedometer, telling you your speed at every single moment of the trip, could you use all that speed data to figure out the total distance you traveled? The answer is yes, and that process is called integration.
So if we know a function's rate of change, its speedometer formula, is 3x squared plus 4x minus 5, our accumulator tool can actually work backwards. It can reconstruct the original function that it must have come from.
But what's that little plus c at the end? Well, that's the one piece of information we just can't get back. Think about the car trip again. If you only have the speedometer data, you know exactly how far you traveled, but you have no idea where you started from. That c is our unknown starting point.
So let's step back and just look at the 3 amazing tools we've just put in our mental toolbox. They might seem a little abstract at first, but they really are the keys to understanding and building the world around us.
So we've got the derivative, our math speedometer for finding rates of change and those all-important peaks. We've got matrices, the ultimate organizer for taming really complex data. And we have the integral, our grand accumulator for adding it all up. Each one is a specialist, but together they're just incredibly versatile.
You know, Galileo said it best hundreds of years ago. This stuff isn't just a game we play with symbols. It really seems to be the underlying language that describes everything, from the way planets move to the way financial markets flow.
Just about every piece of modern technology you can think of, from the GPS on your phone to the engineering of a skyscraper to the algorithms that run AI, all of it is built on these foundational tools. They're like a superpower for solving problems. So the only question left is, what would you build with them?